Swayam Prabha. Digital India. Educated India.
Good morning again and welcome to our course on Introduction to Micromechanical Machining. In the last class we started a topic on burr formation and we understood that burrs are some of the one of the things which is not desirable in the macro machining as well as the micro machining. But we have seen that it is difficult to remove these burrs in the micro machining because of the size limitation, and we have seen some of the disadvantages because of the presence of the burrs, and that will create a problem in the component which is going to use for a different application. So, let us further go into the detail of the burr formation at the micro scale. So, this we have seen in the last class that there are lot of problems because of the burr formation. So, these are the problems of the burr formation. Then what are the ways because of that burrs are forming into the workpiece. So, let us see those things. So, factors of the burr formation. So, one is the tool sharpness play important role, because if you are machining with a blunt tool at that time, we know that your cutting edge radius is very large compared to the uncut chip thickness, and that is the reason you are you are not able to remove material very clearly, and you are end up with the rubbing and the plowing mechanism which we have discussed some time back. Workpiece material, because if you are machining a hard material or the brittle material or the ductile material, every times your burr formation will be different, and whatever parameter we are setting up for a one particular material, that may not be applicable for the burr reduction in the other material, because materials behave differently when you operate under the same condition, and so that burr formations are also different. Then the feed rate also play important role, because if you go with a very high feed rate, at that time you may end up with the high burr. But now what we are looking here, that if you tell that feed rate is high, feed rate will result in the low burr, but that is applicable for a certain material and certain specific condition only. So, there are no any generalized sentences available. That means you cannot generalize anything that low feed rate equal to low burr height or the high feed rate equal to high burr height. So, that is specific for a specific condition and specific materials only. So, generalization of any type of conclusion is very difficult in the micro scale, because we know that there are lot of other parameters are also playing important role, and that is why it is difficult. So, we will see a material point of view in the next few slides, that how this feed rate also play important role. Cutting speed is very important here, because if you go with a low cutting speed and if you are cutting a ductile material, then you are end up with the high burr, and depth of cut, and obviously the chip thickness. So, from this we can understand that speed, feed and depth of cut are always present for any type of optimization or any type of material removal, because these are the three parameters which are required to set perfectly or optimize in such a way that you are end up with a less amount of defects, and burr is one of the defects by which you are not able to use the part directly after machining. You have to go through one post processing operations. So, what are the 6 physical processes which forms the burr? So, one is the lateral flow of material, which occurs whenever solid is compressed, because we know that we are plunging the tool in the workpiece material. So, what is happening because of that, that whenever you are putting a or pushing the workpiece, and this is our chip, this is our uncut chip thickness, and this is our workpiece, whatever we are machining out of it. So, whenever we are pushing the material, we assume that everything is rest of all the chip is flowing over the rack face of the material, but we have seen in that flowing mechanism that some material is actually moving on the side also, that is also creating problem. And lateral flow is, that means some material will also go through the machine surface. So, at that time there is also creating burr formation. Bending of the material, because whenever you are reaching at the end of the position, so this is the end position here. Now, when your tool is reaching to this location, so this is your tool, it is reached to this location. Now, what is happening? The strength of this material is very, very less. So, instead of a clear cutting, what will happen? This particular material will bend and it will become a burr formation here. So, that is also one of the reasons, the bending of material, mostly it happens in the ductile material. Tearing of chip from the workpiece. So, this happens mostly in the brittle material, because now you consider this is the machining of a brittle material, and now there is a crack propagation. So, this is the crack generated during the machining. So, if you continue this crack, so this crack will present here at this location. So, when your tool is here, at that time this crack has already crossed this particular workpiece end. So, this whole thing whatever is available, this will bend here and then it will create a burr formation. So, this is also one of the reasons. Redeposition of the material, that mostly happens in the milling operation, because when you are cutting a slot milling, so at that time, so this is the correct, this is what you want to do a cutting. So, your milling cutter is here, consider that the size of this slot is same as the diameter of the milling cutter. Let me give different colors, that is much better to understand. So, this is your milling cutter. Okay. So, when you are cutting it, at that time what will happen, that when your tool is at the center at this location somewhere, the chip will actually try to accumulate at this location on the top face of the workpiece. Right. So, this sometimes what happens, that your chip is not completely removed, by that time your tool is already moved ahead in the forward direction. So, this is the chip will whatever coming is that will again actually redeposit on the top surface and it become the part of the top burr. So, this is also one of the reasons. Incomplete cutoff, that you are not your tool is not reaching to the end of this position. So, that is also one of the reasons for that, you, whatever you have calculated that this should come, your tool is not completely completing the path of the cutting direction. At the end you are end up with the some material which is left here. So, your tool is not reaching to this location. So, this is the problem at this location. So, that is not enough. So, flow of material into the crack. So, whenever it is doing machining at a brittle material, at the time the crack is propagated and some material is also flow into the crack, and that will become a part of the burrs. So, these are the different physical processes by which you get the burr formation in the machining operation. Right. So, what are the types of burrs? So, here some burrs are given. So, this is called tear burrs. So, what is tear burrs? It is a result of material tearing loose from the workpiece rather than shearing action. So, now if you consider this thing, that when you are removing chip, now you consider your tool is located here. So, this is your tool location, right, and you are penetrating your tool in this direction. So, instead of just a shearing action purely, that your workpiece is getting teared away, because many times it happens in the laminated material, that is, suppose you are talking about composite material where there are different type of layers available, and when you do cutting of this thing, at that time it will always find a interface of the play, and at that time it will create a this type of tearing burr. So, these are called tearing burr. Now, these are called poison burr. So, what is poison burr? Poison burr is a result of a material's tendency to bulge to the side when it is compressed until the permanent plastic deformation occurs. Now, let us consider this situation. Now, consider this one is a tool. So, this is the one cylinder, you are rotating this cylinder, then you are pressing this cylinder inside. So, what is going to happen, that you consider our tool is a blunt tool. Now, when you are pressing it inside, whatever there is amount of press, now consider we are looking from this side. So, now this is the cutting tool and this is the workpiece what we are looking at this location, correct. So, now whatever is this material, because when you are pressing this tool inside, so this is the amount of material it is displaced, it is inside. So, rotation is in this direction, correct. So, when you are putting your pushing this particular tool into this material, this amount of material will try to displace at some location. So, this material is going to this particular location, correct. So, now this is called poison bar. So, whenever you are getting this type of poison bar, so this is because of the displaced material. So, if you continue in this direction, now rotation in this, at that time the high chance that this poison bar will be removed. And this is the rollover bar. So, it is essentially a chip which is bent rather than sheared, resulting in a comparatively large bar. So, this is mostly called the exit bar. So, your cutting tool is here. So, this is your cutting tool and you are going in this direction. So, once your cut is over, at that time what happens, at the end if some chips is available, at that time that chip is actually getting bended over instead of continuously removing out of the workpiece, and your tool is completely passed from this, and so whatever the bending of this chip, so this is called rollover bar. And this is mostly happened, we have seen in the earlier slide also that this was the bar which was created at the end of the cutting tool or end of the workpiece. So, these are the three different ways we can, there are many other ways also we can give a definition to the bars that we will see in the next slide. Now, so this is more comprehensive figure compared to earlier case. So, here this is the slot cutting by milling cutter. So, now your rotational direction is in the clockwise direction and then you are moving in the upside direction, your workpiece is feeding down. Now, your cutting tool is like here. So, now consider, let us draw your, so this is you consider your cutting tool, correct. So, it is rotating in this direction. So, when it is rotating at that time, you consider this is called entrance sidebar and this is called entrance sidebar at this location. So, whenever your tool is entering inside, at that time all the bars are related to entrance part. So, if you consider this is called sidebar, this is the entrance bar because it is at the location which is other than the side. If your, when your tool is moving up, that means in the feed direction, at that time some tools will be some bars will be formed at the top position of this. So, those things are called the top bars. And when your tool is completely exit out of the workpiece, at that time again you can call the exit sidebar, that is on this side, exit sidebar on the right side, and something at the in between this side that is called exit bar. So, we have a 3 entry bar, 3 exit bar and some top bar on this particular side. So, these are the much better definition, because by just understanding the exit bar you understand that that is at the end of the cut, and when you are talking about entrance bar, that is when your tool is about to penetrate into the workpiece material. Some more things are also there. So, these are the some more things. So, this is the one material, because we know that burr formations also affect the different material properties, because if you change the material and change the process parameter, your burr formation will be different. So, you cannot have the same definition for the same. So, every time whenever we are looking at the burr formation, it is better to understand which material it is there and what are the parameter settings. So, now this is the one thing. So, this is the RPM, 20,000 RPM and the feed rate of 1 millimeter per minute, and the depth of cut is a 3 micron. So, what are the different way of telling those things? So, this is the one thing is the primary bar. Primary bar means that is these all the things considered as a primary bar, because that is which you are not able to avoid in that case. So, this looks like a primary, whatever we have shown this schematically diagram in earlier slide we have seen by SEM image, that's all things are called a primary bar. Then another call is the needle like bar. So, where the dimensions are very thickness is very small and it is more sharp compared to the primary bar. So, that is why it named as a needle like bar. And now you consider that that happens when you increase the RPM, you increase the feed rate and you reduce the depth of cut, because when you reduce the depth of cut, your thickness is reduces, and because of a reduction in thickness, your thickness of the bar also reduces. This is called feathery burst. So, it is something like a very woolen type of things. It does not have any perfect shape, but it looks like a mixture of a very small amount of needle like burr. Now, if you see for this particular parameter setting, your RPM is in between the 20,000 and 60,000, feed rate is 4, it is also again in between these two, and depth of cut is 3 micron in this case. And this is called minor burr, that mostly happen if your feed rate and the depth of cut is very small and RPM is also small. So, most of the material is removed in terms of chip, but very small amount of material is left on the top surface, and because of that you are getting a minor burr. So, anyhow whatever is the burr we have to remove at the later stage. If burr formation is very small, sometimes in some application it is negligible. So, you do not need to do any deburring operation, but in this type of burrs where the primary burr and this bigger size of burrs are available, you have to remove those burrs by later stage by some different deburring operations. So, let us see that how the burr formation occurs when you penetrate your tool into the workpiece. So, what are the different stages? So, this particular slide will tell you that before crack propagation how the tool is interacting with the workpiece material. So, this is the first thing. So, it is a continuous cutting. So, what is continuous cutting? That is a proper cutting of the material. So, you are getting a chip conferred very easily here. Right. So, this is the chip formation, no problem in that, and this is the primary shear zone, this is the plastic zone, and this is the elastic zone. Because when your tool try to penetrate into the workpiece material, at the time you will get a small deformation ahead of the tool movement. So, because you have to, there is a displacement or there is a deformation of the material, the deformation is actually inside the material. It always create one of the ways to facilitate the material removal. That means that the material is not deformed directly at the shear plane, but that is initiated much before the shear plane, and that initiation will continuously convert in terms of the shear plane angle. So, that is what is showing here. So, elastic plastic deformation zone around the tool. So, this is the elastic zone, plastic zone, and this is the shearing zone. So, this is what we need in. So, when you continue in this particular direction, what is happening that your whatever is the plastic zone and elastic zone, that will try to propagate. Now, this is the end edge of the workpiece. What? Because we know that mostly burrs are formed on the top surface or the edge of the workpiece. So, this is what is happening. So, your plastic zone will try to go, or it will expand in this direction, elastic zone is further expand, and this is the what is happening, the elastic zone reaches to the workpieces. So, now once, because now it will, you are continuously pushing your tool in this direction. So, because of the pushing you are expanding the elastic plastic zone also, and once you continue this thing at the time, because we know this is the edge of the workpiece. So, your elastic zone will reaches to the cutting edge of the or the edge of the workpiece. Now, in the third step it is initiation. Why it is called initiation? Because now this is the plastic zone, and again there is one more plastic zone occurs, because now if you see this particular thing, now this is bended little bit. Now, see this particular thing, this is right angle, but now it is a bending. So, now this particular thing is called the nucleation. That means where your plastic zone also occurs here, because now whenever you are pushing this material, your material start deforming from the other side, because now whole thing is a plastic zone now here in this particular location. So, plastic zone reaches to the workpiece edge, and this particular plastic zone deformation at the workpiece edge at the plastic as plastic bending. So, now your workpiece start bending in this direction, and because of that you will again get one more plastic zone at this location. Now, in the next stage what is going to happen, this particular plastic zone will try to connect with each other, because as your tool is further moving inside, now you can see in this particular diagram. So, now what is happening, that now this whole thing is a plastic zone now, and now it is a pivoting. Pivoting means it is a initiation of the deformation, large deformation. So, now what is happening, that whatever the shear zone is there, that you will again get a shear zone here at this location, but it is not because of the cutting tool interaction, but because of the bending of the workpiece. So, now what is happening, that large deformation like catastrophic deformation occurs at the workpiece edge. So, that is this one, this is the thing, and cutting force may start decreasing, because now what will happen, that your total resistance of the deformation from the workpiece reduces, because now you are getting one additional deformation That is from the workpiece side, not from the tool side, because now this deformation again this whole thing will become little bit soft, this whole thing part, and our objective is to cut from here to here. This is the what is our objective, right? It should move like that, but it is not happening here because you are getting one under deformation the plastic zone here, and because of this thought. So, now if you continue, this whole thing is in more unstable situation. Now, if you further go in this direction, now large plastic deformation at the pivoting point expands to contact with the deformation in the primary shear zone. So, now whatever this particular location is there, this particular zone, this will try to connect with this particular part, because now you are getting one additional deformation here, and this is also deformation. So, your tool continue in this direction, this direction, this direction. At that time your shear plane angle also moves ahead of the tool. At one location this both thing will match, and once the matching is over, now we can understand that how things are different for a different material, brittle material and the ductile material. So, now this is the cutting line. So, our objective is to cut the material from this line. So, this is our objective, but now we know that our objective is to get this workpiece, correct. So, this is our workpiece, but we have already got something which is extended beyond the workpiece edge. So, this particular thing is the burr. So, now characterization of this particular burr is different for the brittle material and the ductile material. So, let us see in the next slide how these things are different. Now, so now earlier slide was the before the crack propagation, and now this one is the with crack propagation. So, let us take this particular image again to the next slide, and so we can understand what things are. So, this is the earlier figures whatever it has created here, correct. So, this is the same figure. So, now our objective is to cut material from this, but and this also. So, this is the extra thing, extra material, alright. So, now we have two zone, one is the ductile material. What is going to happen if this particular crack is in the ductile material, this is the brittle material, correct, right. So, what is happening in the ductile material, because in ductile material it has a large critical fracture strain, because it does not fracture very easily, and strain in the negative shear zone is smaller than the critical strain of the material. So, wherever this is the particular shear zone, so whatever this is the shear zone, now because it is extended on the edge of the workpiece, so strain in negative shear zone is smaller than the critical strain of the material. So, material will not actually separated out very easily compared to the brittle material. So, now let us go in this direction. So, if it is a material cracks in this case, so now there is a crack initiation. So, now this particular crack whatever this dash line is showing, so we expect that a material should move in the same direction, because it is a ductile material, you are not getting a fracture of the material. So, unless the tool is completely passing through the workpiece, you will not get a chip out of it, it is still sticking to the surface. So, this is the crack initiation, the crack initiate along the cutting line. So, this is the crack initiation in this line, and this is the negative shear zone what we are talking here. So, it is a smaller than the critical strain of the material. So, it will not exceed the particular strain of the material. So, it will stay there. So, crack growth along the cutting line. So, now whatever is this, the crack growth in the cutting line, it is continuously in this direction, and this is the cutting line, the large deformation zone, that is what we have started with this particular location. And once your tool is passing through this part, your chip is coming out of that, and whatever is this part, so this part is the burr, because this is the extra thing whatever you wanted. This is our objective to get something like this, but we are getting something like this. So, this is the burr formation in the ductile material. What is happening in the brittle material? Brittle material situation is completely different than this, exactly opposite, right. So, here the small critical fracture strain, because it was large here, because brittle material it will fracture more quickly, and whatever is the negative shear zone, strain in the negative shear zone is larger than the critical strain of the material. So, now how these things are different? Now, if you follow this particular line, cutting line, right. So, our cutting line was this one, and if you consider ductile material, your material is removed through the cutting line, correct. But what is happening here, that we have a critical fracture. So, now instead of that, because now if you say this is the material which is not completely sheared, that means still somewhat, but still your tool is moving in that direction. But here what is happening, that crack initiate along the negative shear zone, because now this whole thing is a shear joint, and if you are moving, so this is not, this is comparatively hard material compared to this soft material, because in shearing zone your material becomes more and more strained. So, your crack which should be in this direction, now it is moving in this direction, because now this is the easy path to follow while removing the material. So, if that is the case, if you continue, now your tool is penetrated, now crack is propagated, now that is the thing what is happening in the brittle material. So, this is called crack propagation. So, crack grows along the negative shear zone, right. So, shearing mode converts into the opening mode. So, now that is opening. So, now this particular thing will try to open now, because if it continues in this direction, it has to remove so much amount of material, but now here in this location, at that time your material removal requirement is very, very small in this case. So, now when it is coming out of that, here now you see the difference, how much is the difference. So, this is the amount of material which was staying in this particular ductile material, but now we know that our crack propagation is moved in the different direction compared to the cutting line. So, now this much amount of material is removed, and this part of the workpiece whatever is written here, that is called foot. That is one researcher has given the name, that is called the foot bar, and this is called the breakout. So, now it is a breakout, because the crack is initiated in this location, and because of that you are getting a chip out of this part, but still there are some burrs available. Now, how these things are different in both the cases? Now, consider two situations here. This is our objective, that this should be the workpiece, but here we got one additional part, correct. So, now if you apply a deburring operation here, there is a still chance that you can get this workpiece out of it, correct. This is because you remove this part, you apply some type of lapping operation or some type of cutting operation, then you can remove those things. But problem is here, because now our requirement was this much, correct. This was our requirement. So, even if you apply some deburring operation or something, you can remove this much amount only, but there is no material at this location. So, even if you apply deburring operation, what is going to get here, this is what you will get, correct. So, this is dimensionally inaccurate. So, if you consider ductile material machining and you end up with this type of exit bar, at that time there is a chance that you can still use this component with a condition that deburring operation does not destroy the actual component, it removes the bars only. But in this particular case, where the some amount of the material which should stay onto the surface, but it is also removed as a part of the chip, then you are actually getting a dimensionally inaccurate component. So, if this particular thing is some functional requirement, then it will create a problem. But if it is not functional requirement, then here what happens, that your burr removal operation is very, very less, because the burr formation is very small compared to the ductile material in the brittle material. So, in this case your reworking will be less, only if this whatever is material removed from this location does not have any functional requirement. So, these are the two different ways by which we can remove the material, but it is not the only thing. Now, if you see that this is correct for a one particular setting of a speed, feed and depth of cut, right. If you change this particular setting, then you will get a different phenomena or schematic at a particular instant. So, these particular parameters play important role. Other than this parameter, what is the material homogeneity, what are the defects. Now, consider even if it is a ductile material, you will get some porosities in this location, then this ductile material will also actually move along the brittle material, whatever way it is moving in this direction. So, in that case, that means whatever we are showing here, it is a very, very generic idea, and it should not be actually copy, or it should not be understood for the different materials, because we know that if you change the material, if you change the material property, everywhere this particular mechanism will change depending on the conditions of the machining operation. So, let me finish this class here, and still we have some slides on this burr formation. Those things we will discuss in the next class. Thank you very much.